to 5 from competence. Tomorrow in the morning you will have databases. Then in the afternoon you will have open. Right? So I hope that you will get achievement out of this work. Right? So do not think that this will anything we discuss which is biased to the examination that you already had. So we give general idea, general understanding of the subject. So take it in that attitude. This subject is mathematical computing 1, and as you know, there are several chapters in this subject. And let me discuss the logic first. Logic and set. If I have time, I will go through briefly relations. And as you know, the logic it is related to some kind of for example, the argument. Right? You all have made some argument among you. Right? So how do you do the arguments? So what are the objects that you are using in that argument? The object that you are using in that argument is mainly the sentence. Right? You all agree with me that you use sentences. Right? Whereas in your school time you learn in your school time you learn real number set. Right? So for 13 years you learn real number set. There the object you handle is real numbers. Right? But this is very much different to this real number set. Right? So this is called algebra of propositions. In logic, you handle proposition. What is proposition? Proposition is a statement, but we don't call all the statement proposition. Right? So it must satisfy certain property to call it is a proposition. Right? So let me define the proposition. The proposition is a statement or sentence where you can determine the truth value of that. Right? Any statement or any sentence, any proposition must have one of the truth value, true or false, nothing else. Right? So there are some sentences which can have at the same time true or false, right? Which are a little bit complex. Right? So we learn under this logic just the casual logic, right? Where we consider only the sentences which can have true or false value, right? Right? The proposition is a statement or sentences that is either true or false. For example, out of this, what do you say about the first one? Is it a statement? Is it a proposition? Is it a proposition? Yes or no? Yes, because it is a It is a sentence, right? Which has a subject, object, and the verb is a complete sentence, right? It's a statement, and also you can tell the truth value of that exactly, right? You can determine correctly what is the truth value of that one. How about the second one? 2 is not an integer. That is also a proposition. And is 2 an integer? It is not even a question, sentence. It is a question. And also, there is no point of finding out whether it is true or false. It is pointless, right? So, it is not a proposition. How about this one? X squared is greater than equal 10. It is completely correct sentence. But we cannot determine the truth value unless we know what is X, right? So, any sentences which has the variable is not considered as proposition, right? Similar to this one, right? And 5 plus 3. 5 plus 3 is not a complete sentence, right? It's just the expression. So we cannot determine, we can't determine truth value. We can't say true or false, right? Write your answer on the blackboard. It's a command. It's not a sentence, right? So again, there is no point of verifying whether it is a true or false. Pointless, right? So now you know. Now you can confidently determine whether the given sentence is a proposition or not. Right. Since each proposition must have a truth value, true or false, let me use to represent these two values, T for true and F for false. Right. So that is, this is true, this is false, right? This is not a propositions, and we can't decide the truth value of these three, right? Only these two. Right. Now, if I give you the example of a proposition, another example of proposition, for example, I am teaching. Is it a proposition? Yes, it is sentences, and it is true, right? So it is called a primitive proposition. It's a very simplest form of proposition, right? But usually we don't deal with all the time primitive propositions, right? Practically, even when you argue with your friends, right? You never use only the primitive proposition, right? You use set of sentences to convince that person, right? You can't convince person on certain thing only using one primitive. You have to use set of primitive proposition, right, to convince something. So therefore, usually we deal with compound proposition. So what is the compound proposition or composite proposition? Both are same. Compound or composite proposition is a proposition, is a statement which can be further divided into sub-statements, right? Whereas the primitive proposition cannot be further divided, right? So that is the main distinct difference between primitive and composite proposition. Now, it's very easy or it is straightforward to determine the truth value of the primitive proposition, right? Very quickly you can determine the truth value. But in a compound proposition, it's not straightforward, right? For example, this is the primitive proposition. Now this is the example of a compound proposition, right? Why this is the compound proposition? This can be further divided into sub-statements. For example, this one you can subdivide it into two primitive propositions, right? But the truth value of the primitive proposition can be directly determined. But here you need to do some work, right? It is not straightforward. But this one sometimes you may be smart enough to quickly determine the truth value. But I can form, or you can form, more and more complex compound proposition, right? So to find out whether this is true or false, it's not straightforward, right? You have to sit down and you have to work out on a piece of paper, right? And spend about, I think, 5 minutes to find out whether this is true or false, right? So that is the complexity in compound proposition, and you have to deal with this compound proposition when you are dealing some using apply some logical reasoning to convince something. Right. Now first thing you should know how to determine the truth value of the compound proposition, right? Whatever complex is it. But before that, let me introduce some basic truth table, right? You can use this basic truth table to determine the truth value of any complex compound proposition, right? So before I introduce the basic truth table, let me introduce some concept, right? Now in an algebra proposition, similar to the algebra of real numbers that you learn in school, right? What are the operations that you use in your family real number set? Summation, multiplication, addition, subtraction, division. So those are the operations there. So you don't find that operation here, even though this is called algebra of proposition, right? So what are the relevant operations here? You already familiar with that. A given sentence, you can make it a negation of that one, right? So that is, I use the symbol to represent the negation, this symbol, and also you can join the two sentences using and, right? Not only and, using the O, right? So not only these three, there are some other connectives, some other operations. Let me give these three symbols to represent these three operations, right? These are some examples that the expression that you use in natural English can be converted to the logical expressions using those connectives, right? So usually you use this negation to replace anything that you want to express some idea about the negation, right? The negation can be expressed in different form. You may say that it is not true to say that I am teaching well. Sometimes you can say that it is not false. It is false to say. It is wrong to say. There are different ways of expressing the negation, right? So whatever it is, you should be able to identify whether this is a negation or not, right? If it is a negation, use this symbol, right? For example, this one is converted with this one. So this means what? It is false, or it is not true to say University of Colombo is in Madras, right? Let me skip this one. Right, conjunction. Right. So this and symbol in logic, it is called the conjunction. Right. Now, how we read that one? For example, this one. 2 is not an integer and cat is an animal. This compound proposition is in fact the conjunction of two primitive proposition. Right. So it is a conjunction of the two proposition, this one and this one. Right. So we represent that as this, similar to the disjunction, right? So this statement is a disjunction of two primitive propositions, right? So this one and this one, it is represented like this. Right. Now before we handle more and more complex algebra of proposition, let me introduce some more concepts. Similar to the real number set, how you represent the real numbers, any real numbers with some variables. You need some variables. For example, to say that x squared plus y squared equal r squared is a circle, right? You can't use the real values, right? So you have to tell that using variables. Like that one, in logic also there are some results. Right? To express that one, you don't use actual statement. Right? So those results exist for any type of sentences. Right? So let me use simple letters, p.q.r.s, simple letters, to represent any proposition. Right? So keep in mind that when I use the p.q.r.s to represent any proposition and state any results, keep in mind those propositional variable can be replaced by any sentences. Right? Still that results form. Okay? An expression involving logical variables. Right? For example, this one. So this is the expressions involving logical variables, p and q. Right? It can be more than 2 with connectives. Right? So you can create a logical expression using proposition connective. So this is one example. So this type of expression is called, that proposition is in propositional form. Right? Right. Now let me introduce the basic truth tables. The truth table is a computational device by which we can determine the truth value. Right? So it is a tool. Truth table is a tool that you can use to determine the truth value of any complex compound proposition. Right? It is very strong tool. Right. So this is the simplest truth table. That is for the negation. Right? So negation, the P is any proposition. Right? When you create the truth table comprises of rows and columns. Right? So in column you represent the propositions. In rows you represent different combination of truth values for that given proposition. For example, I use P. Right? I want to determine what is the truth value of negation of P. Right? Now I use P, then I have to write it down. Right? First of all, you write the P, and P can have different truth values. Right? Write it down all the possible different truth values of P, that is true and false. So these rows should represent all the possible truth values that P can have any given time. Right? So identify the proposition in the given expression, then identify the rows. How many rows you need? The number of rows is equal to number of possible truth values the P can have. Right? It can have only 2. So denote that one. Right? So then you want to finally find out the negation of P. The negation of P is the opposite truth value of the truth value considered. Right? If this is true, this is false. If this is false, this is true. So keep that in mind. Now, truth value of the conjunction. So this is the conjunction. This is the simplest truth table for the conjunction. So this involves, this composite proposition involves two distinct propositions, which is P and Q. Right? So then once you identify all the distinct propositions there, you write it down all the possible truth value combinations. So at given any time, these two can have only these possible truth value combination. Right? So for these values, the truth table says what are the truth values the P and Q can have. Right? So according to this table, this conjunction becomes true only when the components become true. Both components become true. Otherwise, it is false. Right? So this truth table is very familiar to you. Right? Now look at the next one. Truth table for the disjunct. So when it becomes true, when it becomes false only when both components become false. Right? Otherwise, it is true. Right. Now those are the simple truth table. Right? Simple truth table means so that represents truth value, determining truth value of most simplest composite proposition. Now thing is that once you are given any composite proposition, for example, something like that. Right? Determine the truth value of this one is not straightforward. Right? So how we can determine truth value of this one? This can have how many distinct propositions? 3 p.q.s. Right? So first of all, you need to find out, identify the distinct proposition this can have. So then you have to decide how many possible truth value combinations. What are all the truth value combinations p.q.s can have at given any time. Right? So one of the combination is true, true, true. Like that one, there are other possibilities. So you have to identify all the possible. How many possibilities there? 8. Right? If this compound proposition has three distinct primitive propositions, the number of possible truth value combination for 3 is 2 to the power 3. Right? If this has n number of distinct propositions, it is 2 to the power n. Right? So you know how the number of rows this can have, 8. So you have to carefully list out all these 8. Right? For a 4, sometimes even you don't use any pattern, you can verify if you miss something, where you miss it, you can correct it. But if it is 8, if it is 16, if it is 32, unless you use some form of pattern, if you mix any combination, it's very hard to go back and find out where you miss it. Right? You lose much time to edit that one, correct that one. So therefore, use some pattern. The pattern that I am using, I fix these two, and I consider all the possible values of s. Right? So then I change this. I considered only the true value for q. Let me change only this. This is true. This is false. The other value of f. So then I change this again. All the possible values of f by keeping this is fixed. Now I change this. Right? And do the same thing here. Right? True, 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 false, like that. So follow some kind of pattern that guarantees that you don't miss any combination. So once you complete that one, then you can determine this. But even you work out all these, you cannot straight away determine this. Right? Can anyone say what is the truth value of this one when p.q.s take the values t, false, true, false, true? What is the truth value of that? What is the truth value of that? Not straightforward. Right? Sometimes you take 5 minutes to work out that. So to make sure that you correctly determine the truth value of that one, you can further extend this truth table to represent the intermediate columns. The number of intermediate columns needed is depending on the complexity of the given proposition. Right? For example, it is now you can determine how many or what are the intermediate column you need by analyzing this. Right? If I ask you to find the truth value of this one for given combination of truth values, which one you determine first? The parenthesis, right? The parenthesis. This one you determine first, P and Q. So you can decide you must have intermediate column for that. Right? Without determining this value, you cannot proceed. Right? Once you determine this row, this column, then you can determine this one. Right? So once you have that one, so this is the negation of this. Right? Negation of this. Once you determine this one, then you can determine this. Right? O. Right? So that is the disjunction of this one and this one. That is this one and this one. The taking the disjunction of two columns straightforward. It is similar to the basic truth table for the conjunction. Disjunction. Right? So then this one. So still I haven't introduced that one. I will come to this connective later. Right? So I am considering this one. Right. For that one, I need first to determine this, then conjunction, then finally this one. Right. That's how you complete the truth table. Right. With this one, you should be able to work out truth table for any compound proposition, whatever complex it is. Right. Right. Now look at this one. The given statement, the proposition in English like this, will you be able to convert that into the propositional form, the symbolic form? And keep in mind the logic deals mostly with the symbols, not with the meaning. Right? For example, it is now this one. How do you given two primitive propositions as it is hot, P for it is hot, and Q for it is sunny. How do you represent these using P and Q? Can you just write it down? Yeah, work out all three. Right, good. Right, first one. It is not hot, but it is sunny. Right, keep in mind that this word "but" is similar to the "and." Right. Second one. It is not both hot and sunny. It is neither hot nor sunny. Anyone had different to this? Just as that, I just comment the thing. Yeah, it is neither hot nor sunny, right? So what that no means there? N-O-R, no. Right? The but and the no is a different form of and. Right? So depending on the context, sometimes you have to replace the but and with the but, sometimes and with the no. Right? So this is not disjuncted, is a and. Right? Can you pass that? Yeah, you are correct. But I have to come to that later. Right? There's an alternative for the B. In fact, it's not alternative. This, right? This one, right? This also correct, right? Now, this comes from the relational algebra. Right? When I come to the De Morgan's theorem in the relational algebra, I will explain you that. Right? Now, for the moment, keep in mind that this is also correct representation of P. Anything else? Which one? Same. Huh? Third one. Third one is also same, no? Right? So I will come to that later. Right? That comes from relational algebra. Right. Another common proposition is not a proposition. The expression that you are familiar with. Y less than or equal to 5. So this means is a disjunctive, right? Y less than 5 or y equal 5. Right? So this is a very compact form of this comprehensive disjunctive. And how about this one? So this is the same as this is the disjunctive. Right? Is it greater than or equal to 5 and less than or equal to 10. So now you know what is the difference between the disjunctive and conjunctive. Completely different, right? So it is justifiable from its truth table. Right? Truth tables are different. Right. Now look at this one. An essential concept of the symbolic logic. So that is a characteristic of logic, that we don't deal with the meaning, we deal only with the symbols. Right? Essential concept of symbolic logic is that the truth value of forms propositional forms depend only on the truth value assigned to each of the variables, not on the particular meaning of the proposition represented by those variables. Right? We only deal with the symbol. For example, this one, either rice grows on trees and Pidutaragal is the highest mountain in Sri Lanka, or it is not true that the dinosaurs is extinct. Right? So if we look at only the symbolic form of these expressions, I can have only three distinct primitive propositions to convert this into the symbolic form. Right? If I represent by P this one, and Q by this one, and R by this one, and you know the truth value of this. This is false, this is true, this is true. So then this is the equivalent form of this. Right? So then you can apply truth table to determine truth value of that one. Right? So we determine the truth value not based on the meanings, but based on the symbolic logic. Right, out of this proposition, right? Now you can imagine that how many propositions in this word, right? It is infinite. For example, if I assume here around 250, if I ask you to form a compound proposition using p.q.r, and the connective, negation, conjunction and disjunction, I definitely get different compound proposition from all of it. There would be 250 distinct compound propositions that you create using only the p.q.r. and the connective, not and junction, conjunction and disjunction, right? But can you now? It is not. There's a high probability that even you form completely different compound proposition, there can be some compound proposition that you create which represent the same thing but in a different form, right? So we need to work out and see whether even though it look like different but it represents the same idea. You know, in English same thing can be expressed in different form, right? If I ask you two person to go and complain on something to our director, right? Certain thing to complain. One person complain in one way, another person complain in another way, but both complain the same thing, right? So like that one, you can, out of all the compound propositions that you create using this distinct p.q.r. proposition, there can be some group of proposition which represent the same thing, right? For example, the tautology, right? The tautology is also a proposition. It is also a proposition which has special property. What is the special property the tautology can have? It always true. It never becomes false. That is possible, right? So you can give me an example of a tautology that it never becomes false, right? So like that one, for example, using one proposition, right? Using one proposition, you can create the proposition like this. And if you work out the truth table for that one, you realize that whatever the truth values the p can take, always this becomes true, right? So this kind of thing is called tautology. The contradiction also the group of propositions, right? Special group of propositions, right? This proposition never become true. It always false. It is called the contradiction. Now this is the example of a contradiction creating using only one proposition, right? Right. Now so far I have introduced three connectives. What are three connectives? I introduced negation, conjunction and disjunction, right? So there's another connective called conditional statement, right? So the conditional statement also very familiar to you, right? Whatever the statement, whatever the opinion, view, idea you express using condition. For example, if it rains today, I won't come for the lecture, right? So that is a conditional statement. What you want to say is conditioned to something, right? So it cannot be determined what will happen. It is conditioned to something, right? For example, now when you say that this conditional statement is also a proposition. Why is a proposition? Why the conditional statement like that is a proposition? Because it is a complete sentence, right? And is a compound proposition. Conditional statement is a compound proposition which has the two primitive propositions, right? And you can determine the truth value of that one. Now, how do you determine the truth value of the compound this conditional statement, right? So before that let me introduce the notation that I use for that one, right? The conditional statement can have this form: if P then Q, right? So this also can be denoted by this symbol, This means if P, then Q. Right? So this is the conditional statement because the truth value of the statement Q is conditioned on the truth of statement P. Now this is the basic truth table for that. Right? Now some of the things you agree with me, but some of the things that sometimes you may have confusion on that. Right? For example, now in this conditional statement, usually we call the statement primitive proposition or compound proposition on the left hand side of this symbol is a condition, and the right hand side is a conclusion or result or response. Right? Now when the condition is true, this says condition is true, conclusion is true. Right? Then this truth table says this statement, this conditional statement is true. The conditional statement can have two parts, condition and conclusion. Now this take the different truth values this condition and conclusion can have. When they can have true and true, this condition statement is true. Right? How about this one? This one says condition is true, but the conclusion is false. Right? When the condition is true and the conclusion is false, this tells your conditional statement is false. Right? So having known this now, don't make any false conditional statement to your friends. Right? For example, let me say this: if I win a lottery, I will buy you a car. Is it a conditional statement? Yes. What is the condition? What is the condition there? I win a lottery. What is the conclusion? Buy a car. Right? So buying a car, I put in a condition. It is depending on whether I buy or not, depending on the condition. Now how do you decide whether I am a liar or not? Still you don't know. Right? So that is the characteristic of conditional statement. You can't determine it is true or false. Right? Sometimes people use the conditional statement just escape from the situation. Right? Because it can be determined later. Maybe 1 week later, maybe 1 month later, maybe 1 year later. Right? It is safe to use the conditional statement. So when you determine I am a liar, when you say that what I said was wrong, I am a liar. Only I know I am a liar. Right? But how do you know that I am a liar? You have to wait some time. When you? Sorry? No, I don't buy a car. When you say that even I don't buy a car, I am not a liar. Right? So when you say exactly I am a liar, right? Yeah, wait condition should be true, right? Wait until I win a lottery, then see whether I keep the promise. If I don't keep the promise, then I am a liar. Right? You can directly decide on that. Right? So you have to wait the condition true to determine whether this compound proposition or conditional statement is true or false. Right? Now look at in that truth table. Conditional statement become false only at one stage. That is, condition is true, but conclusion is false. Otherwise, it is true. Otherwise, it is true. Now look at the third one. Condition is false. Right? Even I don't win a lottery, right? Condition is false. I can buy you a car. Right? So nothing wrong with my statement. Right? So I didn't win a lottery, but still I buy you a car. Right? That condition is still that condition statement is true. How about the last one? I didn't win a lottery, and also I don't buy a car. Nothing wrong with my promise. Conditional statement is still true. Right? So when the condition is false, conclusion can be anything, right? You can make any conclusion, still your condition statement is true when the condition is false, right? So now you are more safe. Using the false condition, you can make millions of props, right? This is another example of that one. If you come to work on Monday morning, then you will get the job, right? This is the interviewer promise to the candidate, right? So candidate leave the hall with some hope, right? So I leave that for you, right? On what circumstance can you claim what the interviewer said is false? It's there. Just go through that one lesson. Right. So P implies Q means if P is true, then Q follows. Right. So there's a different way of interpreting this symbol. It's logical true if the truth of P implies that Q must also be true. Right. Last connectives. Right. Last condition is this is the last condition that in your course you have to learn. There are other connectives, right? Some more complex connectives, but I don't want to get that into discuss here. Biconditional statement. As the name specifies, biconditional means there's a condition on both directions. Right? Some of you are familiar with that also. That means when you say something, if and only, when you express something, you put more stress on your condition. If and only, condition happen both ways, not only one way. Right? So you can put this dependent condition for my example. If I win a lottery, I buy you a car. Right? It is only one direction. If I buy you a car, I won't win the lottery. Right? So certainly you can't put both directions. So this biconditional statement is represented, denoted by this or this, and you read this one as P if and only if Q, right? Now interesting thing is, what is the truth table for that? Right? Now truth table for this, now what it says. So this is the truth table, and according to this one, you can identify the main behavior of this biconditional statement. Now look at where it becomes true. It becomes true only when both components become true. Both components take the same truth value. Whether it is true or false doesn't matter. Right? If both parts take the same truth value, yeah, true, true. Here false, false. Then this if and only if condition becomes true. Otherwise, if these different components take the different truth values, this if and if condition you cannot say. Right? It is false. But keep that in mind. Another, sometimes you can guess another. You can view this if and only if in a different way. Take P imply Q. What is P imply Q? It become only false here. All other places true. Take the Q imply P. So this becomes false only at Q is false, P is true. Q is true, P is false. Here. All the other places this is true. And this is P if and only if Q. Right? In fact, this is the this can be viewed as a conjunction of these two. Right? Conjunction of these two. P and Q and Q and P. This is the same as this, right? You can check, verify by taking the conjunction of these two. Conjunction, right? True, 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 false, false, true, false, false, true, true, true. So this becomes true only when here and here. Right? Keep in mind, the if and only can be considered as a conjunction of respective two conditional statements. Right. This is also some kind of a concept, the notation. Now there is a you can form, right? Like I said, given two propositional variable p and q, right? So you can form different compound proposition, right? Right? Set of proposition that can be created using only two distinct propositions can be grouped into this group. Right? This represents set of proposition created using only p and q. Right? This is set of proposition, the group of proposition created using three variables. Right? Now this is just the notation. Right. Now can you remember that I said if I ask you to create a compound proposition using three propositional variable p.q.r, you might all create 250 different compound propositions. Out of that, there can be some of the compound propositions that you created. It looks different, but actually it represents the same thing. Right? So we call it those different form of compound proposition which look different but represent the same thing. We call them logically equivalent. Right? So we can't call it equal. In real numbers, you can straightaway use the equal sign because you deal with the complete equal. Here it is not equal because the form of the compound proposition is completely different. But the only equality is the logical values are same. Right? So given two compound propositions which are in a different form with three variables, right? I can assign any combination of truth values for this p.q.r, but both take the same value at any time. Right? So they look same, they represent the same thing but look different. So therefore I don't use equal, I don't say these two logical propositions, compound propositions are equal. We say it is logically equivalent because we only deal with the logical truth values. Right? So the p and q, right? P and q represents two different compound propositions with the variable this, and we say logically equivalent if they have the identical truth tables. Right? Identical truth tables. So when their truth tables are identical, we say they are logical equivalent or they are logical identity. Right? The logical identity. In logic, right? In mathematics, in logic, the logical identities play major roles. Right? It plays a major role. People, mathematicians, they need logical identity to solve some of the problems. Right? For example, P imply Q, right? And you know that this is logically equivalent to this. This is a well-known result, right? So this is logically equivalent to this one. And what is the difference? What is the advantage of this one? This is the conditional statement. This is the disjunction. And if you want to eliminate this conditional statement, you can eliminate with the disjunction. Right? So these two tell you can express the same meaning in different form. You can express it conditionally or you can express the same thing with the disjunction. right? So this converting, eliminating this type of complex connectives, right? Connectives without damaging the meaning. If you want to eliminate this symbol, you should know the logical identities, right? So you can apply this when you need, right? So this kind of changes people use in artificial intelligence, right? So they need to artificial intelligence or prologue or logical programming. They deal with this logic, right? This proposition, and they don't deal with implication, condition statement, and by condition statement they have to always convert that to the conjunction, disjunction, right? So that is the advantage. We'll take more logical identities. Right. This is one example. I leave that for you to work out how to verify these two are logical. They are logical identities. Now these are well-known logical identities, right? So you can create your own logical identity. You should be able to create, but these are well-known, well-established logical identities. In fact, this is one of the results on which this relational algebra built on, right? So that comes as a logical identity, and you can consider that also as a theorem. This is called what distributive law, right? So there are two distributive law over algebra of proposition. So this is one of the distributive law, right? I will tell you the rest later, and I leave that for you, right? How you verify these two are logical identities? With truth table, right? Create a truth table for this, create another truth table for this, and see what are the values it takes. If it is identical for the same truth value combination of p.q.r. all the time, then we say they are logical identities. Now look at another logical identity. P imply Q is logically equivalent to not Q imply not P, right? So these kind of thing you need, right? Sometimes there is an advantage of telling the something not in this form but in this form, or not in this form but in this form. It is depending on what you want to claim. The lawyers are very smart on that, right? Right. Now this is how you find out. Now you see, now whatever the PQ for all the truth value combination of PQ, these compound propositions take the same truth value. So therefore they are logical identities. These are some of the logical identities, right? So later you realize this is the distributive law over conjunction. This is the distributive law over disjunction, right? I will come to that later, right? For the moment, use the truth table to verify they are logically equivalent. Right, now I think this is the right time for me to introduce the most important logical identities or laws in algebra of proposition, right? On which this field built on. The very big fields, right? Logic. The logic is built on this set of results or these set of logical identities, right? Now these two, right? This is the disjunction of the same proposition, right? It doesn't change. When you apply this operation to this, right, nothing happened to this, right? The same as the conjunction. So this is called the idempotent law. Keep in mind. The second one, associative law, right? So there are two associative law. This is the associative law for disjunction, and this is the associative law for conjunction, right? So this says whether you operate this disjunction first or this disjunction first, doesn't matter. Both end up with the same results, right? Commutative law, whether you get the disjunction of P and Q or Q and P, doesn't matter, right? Distributive law, the distributive law over disjunction, distributive law over conjunction. Now you have to keep in mind the pattern, right? Given this one, you can write this. Given this one, you should be able to see this, right? So both way, whatever form it says, you should be able to write the other form. Now there are four identities. So these are the four identities. Complement laws. So the negation is considered as a complement of any proposition. And there are four complements. Now this is the involution law. If you take the negation twice, that will give the original proposition. De Morgan's law, this is very important, right? Now you can take, with the De Morgan's law, you can take the negation inside, right? Only thing you need to keep in mind that when you take the negation inside, the operation change to disjunction to conjunction, conjunction to disjunction, right? And the negation get associated with each component in that proposition. Right. Now there is a confusion that the order of evaluation of the logical expressions. Right. Now for example, this one, p.q.r, in which order you will evaluate? Right. Which one you do first? Disjunction or conjunction? Right. So depending on which one you operate first, this will end up with the different root value. Right. So therefore, since it end up with a different root value, you have to be very careful. Right. But once you put the parenthesis, always parenthesis take the highest priority. Right? Once you do the parenthesis, you have to, it tells you have to operate everything within the parenthesis first. Otherwise it makes confusion unless there is a rule. What is the rule? This illustrates that if you operate this first, it ends up with this truth table. If you operate this first, it ends up with this truth table. Right? There is no parenthesis, right? Parenthesis, you have to operate in this order. The negation has the highest priority, right? Negation has precedence over conjunction, and conjunction has a precedence over disjunction. So this has the highest priority, this has the next priority, this has the lowest priority. However, this evaluation order can be overwritten through the use of parentheses, right? For example, this one, right? So you can show in which order you operate this one by putting the parentheses. So this one you operate first. So therefore you put the parentheses here. The next you operate conjunction. So you put the next parenthesis to the conjunction. Right. Yeah. So let me stop discussing of prepositions at that point, and I will come to that again when I discuss your examination questions. Right. Depending on the time, we have 2 hours. Right. Now let me introduce briefly what is the predicates. Right? Second part of this logic section is the predicates. Right? And this is the most important. Right? So you need the proposition to properly understand the predicates. Right? And the predicate is the most important of all. Right? So wherever in the logic or artificial intelligence, in lawyers, they deal with this predicate. What is the predicate? Can anyone tell me the meaning of the predicate in very brief? What is the predicate? What do you know about the predicate? What predicate does? It describes something. Right? It describes something. You use the predicate not only to describe one thing. There is no point of using the predicate to describe only one thing. You are wasting the power of the predicate. Usually you are used the predicate to describe something in common. Right? For example, here X won a Nobel Prize in 2012. Right? X plus Y equal 10. Now this is very common. Right? So this X and Y represents many things, and not only for the certain things. Right? Usually predicates are used to announce some results, some theorem. Right? It is generally true for many things. Right? Yeah, let me take this one. Now, what do you think about these two? Are they statements, sentences? Are they sentences? Yes or no? X won a Nobel Prize in 2012, 2002. Is it a statement? No. Is it a statement? No. Is it a statement? Is it a statement? I'm asking, take the second one. X plus Y is equal 10. Is it a sentence or is it a statement? Huh? It is a statement, right? Is it a proposition? It's not a proposition, right? Because we cannot determine the truth value of that one, right? Unless you know what is X and Y, you can't tell whether X plus Y is equal to 10. It's true or false, right? Unless you know who is this X, you don't know whether that statement is true, right? So now in the predicate, we handle this kind of statement, right? We handle this kind of statement. Now, the characteristic of the predicate is that it is a statement and it involves variables. Right? It involves variables. Right? So we call that kind of sentences, statements are predicates. So that now is the predicate is a proposition? Is the predicate is a proposition? Is the predicate is a proposition? No. Right? Keep in mind that predicate is not a proposition. Now I put or now the rest of the thing is how to create the proposition using predicates. Right? Because we are dealing with only the statement which we can determine the truth value. Right? If we can't determine truth value, then there is no point. Right? So we'll see how we can turn these predicates into propositions. Right? Then we can use it. Right? Then we can use it. Right. Before that, just let me that you are already familiar with this one. Now this is the set of real numbers. This is a set of integers. This is the set of positive numbers, positive integers, and this is the set of rational numbers, and the last one is the set of complex numbers. And you know how they relate to each other, right? So let me show with one diagram how they related to each other. Let me take this as a set of positive integers, right? Counting numbers, right? And on top of that, I would take integers, right? Counting numbers comes as a subset of integers, and this is Q, this is C, and this is R, and this is C, complex numbers, right? In your school you learn up to here, real numbers, right? All the numbers you handle in a school time. The complex, sometimes some of you might have handled that one, right? I don't want to deal with that. So keep in mind that the real number set, the big real number set is a subset of, comes under the complex numbers. Now take the predicates, right? This one, x less than y, is a predicate. Right? What is the predicate there? What is the predicate there? This. Right? You use the predicate to describe something. What I want to describe here? Less than. Right? You can create a predicate to describe the greater than. Right? Or you can use the predicate to say some color, right? So each predicate, it has some kind of a description that you try to emphasize. Right. Now x less than y is a predicate. So the predicates are given using variables. Since the predicate use the variable, you should know what are the values x and y can have, right? So x and y can come from, the values for x and y can come from different ranges, right? Depending on the range, the predicate behave differently, right? So therefore, it is very important, I will give you an example later, it is very important that you should not write the predicate without knowing the domain, the range of values. Domain means the range of values x and y can assume, right? Now look at my predicate there. When I write the predicate, immediately after that I write from where x and y come from, right? So x and y belong to R, right? So this is the predicate built on real number set, right? You can this predicate behave differently if you define this in the n, right? If you change this R to n, this might behave differently, right? Domain of the both variables. Right, and there is a notation here, as I said, the x and y are right. Just forget about this. So I don't want to use this here, right? Because this notation I use to represent the parameters in this notation should be what? Proposition. But in this case, this represents the numbers, not a proposition. What is the difference between numbers and proposition? Numbers can have only the values. The proposition can have true or false, right? So they have the different values. So just forget about this one, right? And according to this predicate, you know, if I assign some values to this is true, right? And the other one, this is false, right? So once you assign values for this one, the simplest way of converting the predicate to the proposition is assigning some values to the predicate. Right? This is the most simple way of converting the predicate to the proposition. Right? So like that one you can find, given the values for the variable, the truth value. So then that becomes a proposition. Similar to this. Now this is the proposition involving with 4 variables. Right? So you can find the set of values for x, y, w, z, where this proposition becomes true. Right? Why I call this proposition become true? It's not a proposition. Right? It's a predicate. But I am saying that what are the set of values for x, y, w, z? Right? If you substitute x, y, w, z by the set of values, then they become proposition. Right? So you can find out the set of values for x, y, w, z, for which this predicate becomes proposition, and the value of the proposition is true. Right? Similar to this one. I leave that for you. Right. Now let me take the common predicate. Let px be any predicate. Right? The px can be x squared equal 1, or in normal English use, the px can be no, this involves only one variable, right? So let's take this one. Px is a predicate defined on this domain. Right? This can be some range of values, right? Take in common in general a. Then px could be true for all values of a, some values of a, or for no values of a. Now look at another way of converting the predicate to a proposition. Right? Could be true. Right? When you can determine the truth value of a predicate, then that becomes a proposition. Right? If you can't determine the truth value of the predicate, it's not a proposition. Right? Only thing missing is that you can't determine the truth value of the predicate. Now look at the one way of determining the truth value. You can say for all values of a, px is true. Or for some values of a, px is true. Or you can say no values of x, px is true. Right? Otherwise, what is the other way of converting this predicate to the proposition? You take each value for the x, right? Then it is obviously you take the most obvious proposition, right? But we can't do that one, right? In the predicate, we only try to find out the common way of converting the predicate to the proposition, right? Keep in mind that with these prefixes, all values, some values, no values, you can say something about the predicate. Right? You can say something about the predicate. Now, for example, if I say that, if I take the predicate like x is a male, right? X is a male. I describe the x, right? It's a male. So you can take that as a predicate, right? If I write it in very short way, x is a male, or x is a female, right? Like that one we can write many descriptions, many predicates, right? So take this example, X is a male. Right? Now what do you say if I say that for all X in this class, X is a male. X is a male, we can't determine root 12. Can you? No, because we don't know what is X. Right? And it is no there is no point if I take each one and verify the male or not. Then we can determine by pointing out person, you know how to determine the truth value. That's a direct proposition. Right? If I say for this X is a male, it's a predicate, and if I convert that for all X is a male, is it true or false? False. Right? Right. Now without using that prefix for all X, let me use the sum X. For some X is a male. Is it true? For this class, if the domain, the A represents this class, for some X is a male. True. And if I say for no X is a male. Is it true? No. Why is not true? There is one person who is a male. Right? So you can determine if I put those prefixes, all X, some X, no X, right? If this predicate get associated with the prefixes, then you can determine the root value. Right? So when you can determine the root value, it is no longer predicate. Right? It is a proposition. Right? Predicative proposition. Right? The proposition created using predicates. Right? So keep in mind that to convert the proposition that you create into the predicate must have these prefixes. All X, some X, no X. Right, what is the truth set? The set of all elements in A for which Px is true. Right? The set of elements for which Px becomes true is called a truth set. Right? Is some definitions. So let me stop this 5 minutes time for the debate. Right? You can find the truth set of the predicate Px, where the domain of X is a set of positive integers. Right? So remember that is very important. When you get to the predicate, the domain must be stable. Right? Sometimes the predicates are given without specifying the domain. Right? That is wrong. That is completely wrong. You have to do the predicate in the domain. But sometimes you might see, sometimes you give the predicate without worrying about the domain. Why? It is understood. Domain is understood. You don't need to say that A is a set of animals, because it is understood that A is a set of humans, depending on the predicate that you use. Right? If it is understood, you don't deliberately state the domain. Otherwise, you have to deliberately state the domain. Right. Now